Okay, so as I said in the last video, you know, dwarf stars are the vast majority of stars. Then you get giant stars, anywhere between, let's say 10 times the size of the sun to 100 times, and then there are much rarer stars which have more than 100 times the radius of the sun. As we explore what's called the HR diagram, the Hertzsprung-Russell diagram, we're going to find out that these stars, these supergiant stars, are actually close to the end of their lifetimes. All right, so we're going to do that. This is just to show you, some of these, like Antares would be considered a supergiant star. A giant star, Aldebaran, for example, Capella, Spica. Notice Sirius A, and of course the Sun are well, I guess I don't know. I'd consider Sirius A, just a dwarf type star. I don't know. Maybe according to their classification, it would be. Yeah, no, stars have radius equal to or less than the sun. Yeah, it kind of jumps there to 10. So generally, stars that are less than 10 are just considered, just normal size stars, if you will. 10 to the size of our sun. Sort of, solar size stars, I guess you could say. All right, so this is kind of what we were heading towards before. So remember the luminosity. Let me go back a few slides. So luminosity is proportional to the square. It's the square of the distance from the center of the star. This has to do with surface area, and then of course the Stefan-Boltzmann equation gives us that the luminosity is related to the fourth power of the temperature, and of course the temperature has to be in Kelvin. The radius has to be is actually in meters. All right, so if you combine all that, right, that this is the using the Stefan-Boltzmann equation and the inverse square law, you find that the luminosity is actually related to the radius of the star squared times the fourth power of the temperature. So if you know what the luminosity is, okay, so this is really where we're heading. If there's a way of calculating the absolute luminosity, it's important to understand that it can't be just the apparent luminosity. It's got to be on the absolute scale where we put all the stars 10 parsecs away mathematically. Anyhow, if we can figure out what that luminosity is, which of course there is a great way of figuring that out, it's called the HR diagram. Anyhow, we're about to get to that. So if we know what the luminosity is, and we know what the temperature is, of course the temperature we can get from Wien's law, right? Wien's law will give us what the temperature is. If you measure that peak wavelength, of course we found that there's a simpler, faster way of doing that by just using filters on your telescope and just measuring what the wavelength is at the intensity of the wavelength using two different filters. You can estimate where the peak is and figure out what the temperature is. All right. Anyhow, and so from the luminosity that's given to us in the HR diagram, which I know we haven't seen yet, but we're about to, and the temperature, which again we can get from either the peak wavelength or more frequently from two different using filters on the telescope, we can calculate what the size of the star is. I mean, you could actually work out what R is, which is of course the radius of the star. So remember, most stars, in fact, there's so few, like there's a handful of stars that you can directly measure the size of the star. So this is the usual way that we measure the size of stars, is to find the absolute luminosity, find the temperature, the surface temperature of the star, and then use this equation to calculate what R is. All right, so and we are on the HR diagram. Okay, so this was this diagram, Hertzsprung and Russell, two astronomers, came up with, and so here's what it is. Right, this is the idea: is if you plot the luminosity on the vertical axis and the temperature on the horizontal axis. Now it's a little different than the normal horizontal axis that we normally, like, X is increasing to the right, but what we're looking at is actually the temperature of stars, and so the temperature is actually going down in the direction, in the right direction, towards the right, I should say. So the hottest stars are the O stars, then the B stars. So sometimes you'll actually see the HR diagram where they'll just have the stellar classifications along the x-axis. So just like this, right? O through M, and then there's, of course, L and T as well, in more complete versions of the HR diagram. All right, so what we do is we look at the temperature, we look at the luminosity in solar units, where there's the sun, for example. If you draw a straight line from one, you get to the sun. Notice Alpha Centauri is just slightly warmer than the sun, slightly hotter than the sun. The star Sirius A and Vega are much hotter, almost 100 times. Notice the star Arcturus is about 100 times. And then there's another star down here called Sirius B. And notice here Procyon is there as well, and so is Barnard's star and Proxima Centauri. Proxima Centauri. These stars are very, very dim stars. So, like, they're this distance, if you will, well, this luminosity would be 1/100th the luminosity, and then 1/1000th the luminosity, right? So remember, this is a logarithmic scale. All right, and then of course, if you go up, remember this would be like going up 5 magnitudes. You get to a luminosity of 100 times that of the sun. Right, and then you go up, another five magnitudes in absolute magnitude. Then you'd go up another 100. 100 times 100 would give us 10,000. Right. All right. So So that's. Oh, this would be one. I'm sorry. The ones down here. Let me get my mouse. The ones down here would be 1/10,000th. Sorry, I got so 100th and then 10,000th. Right, this would be a 10,000th of the luminosity of the sun. All right, so let's see. So we start. So this was just some of the very bright stars in the night sky, and we plot this on the HR diagram. That's actually not the thing that we want to do. We want to plot as many stars as possible, so they start filling it in, and with more and more stars. Notice there starts to be these patterns. This becomes what I'm pointing the cursor at right now. This is an extremely important pattern. This area here, and we'll see that as they build it. So this HR diagram they're just doing with the 80 closest stars, and this pattern is going to be called the main sequence, and this is extremely important for astronomy. And they labeled it. There it is. Notice our sun is on the main sequence. Most of the stars that you see in the night sky are on the main sequence. Most of the stars in the galaxy are on the main sequence, it turns out. Notice these horizontal lines. These are constant radii. So if anything, if a star is along this line, that would be 100 times the size of the sun. Things that are along this line would be 10 times the size of the sun. And then, of course, this line right here would be the same size as the sun. This would be 1/10 the size of the sun. Then you can go, there's another line, they're not showing it here, but that would be 1/100th, and so forth, the size of the sun. All right, so this begins to, we're actually starting to see, even with just 80 stars, we're starting to see, the main sequence. This region up here is going to be called the giant and supergiant stars. This region down here are called the white dwarfs because they appear white. They're extremely small compared to the sun. Remember, we're almost always going to compare stars to our sun, right? Because that's the star that's closest. That's the star that we know the best. All right, so again, now we're plotting 100 brightest stars. Let's see. So we start to see the giant stars, and then we get to, where are they showing the super giants, or you're not showing that yet. Again, let's see, brightest stars in the sky appear, right, because they're enormous luminosities. Oh, and this is so another way of when we get the HR diagram is we're going to get some extremely hot stars that are really small. Okay, so how do we know that they're small? Another way of knowing that they're small is if they all have if they have the exact same temperature. Like where I have my cursor pointed. Let's say that this is 20,000 Kelvin, the surface of that star. There'll be some stars right about here, where I have the cursor pointed. And then if you go straight up, we're going to encounter some other, like supergiant stars. And the only difference, since they both have the same temperature, so this is actually a general lesson about the HR diagram. If you just draw a vertical line and you find a star way down here and a star way up here, the difference, because they have exactly the same temperature, the only difference that could explain the difference in luminosity, right, the amount of power that's coming off of that star, or those two stars, right? So you compare a star that would be, where's my cursor? Sorry. A star that would be like way down here, and then a star that would be way up here. Again, same temperature. The only difference would be size, right? That's the only way that you're going to get more luminosity in this upper left-hand side of the HR diagram compared to the lower left-hand side of the HR diagram. So size. All right, so we're going to see that in a more complete. So this is the next 20,000 stars, and notice you start to see the main sequence, right? This area here is called the main sequence. It's not exactly a straight line, but notice again we see these lines which show everything that is the exact size of the sun. There's this straight line right here would be 10 times, and then 100 times. This would be 1/10 the size. So anything along this line would be 1/10 the size of the sun. And then, of course, you can get down to 1/100th, 0.01, and then 1/1000th, and so forth. Right, and notice and this is actually very, very true. Just even with just 20,000 stars, 90% of the stars are on the main sequence, and then 9% are these red giants, and then only 1% are these things down here, which we're going to call white dwarfs. All right, and we'll talk about the evolution of stars. We're just starting this journey into understanding the evolution of stars. So this, in fact, since I'm talking about that, that's exactly what the HR diagram is. It's a snapshot of the stars at various stages in their life cycles. All right, so that's a huge idea that allows us to peer into the life cycle of stars, is using this this tool, the HR diagram. This was a huge invention